This video is going to consider series parallel circuits for AC circuits, but we're going to start off here with a DC circuit to just kind of remember some of the fundamentals. So we know for a DC circuit, which is actually also true for AC, that it resistance in series simply add up. So you just take one resistor plus the next one in series plus the next one in series, and so those resistances all add up. If we have a resistor in parallel, then we get this 1 over effect. So we get 1 over R1 plus 1 over R2 and so on, plus 1 over R3, and it just carries on. So those are our general resistances. So what we want to do is we want to take this circuit here, and let's say that we have a 10 volt DC source, and we have one resistor, call it R1, which is a 1 ohm resistor, and this is in series with our supply, and it's then splits. The current's going to split, and we're going to have two other resistors, R2 and R3. And so what we want to do is find the total impedance, which in this case is simply resistance. Okay, so we're going to be actually finding our total, which is the total impedance to the circuit. And so we're going to start here by taking these two parallel resistors and simplifying them into one resistance, one equivalent resistance, that it will be in series with the first resistor. So we're going to have this equivalent resistance is going to be these two resistors. So we just have 1 over R2 in this case plus 1 over R3, and so that gives us 1 over 2 plus 1 over 2, right, which ends up giving us a 1 over 2 halves, or 1, which simply gives us 1 ohm. So now we have a simpler circuit where we have our 10 volt supply feeding R1, which is 1 ohm, plus this equivalent resistor, which is also 1 ohm, and returning back. Okay, so this is what we call an equivalent circuit that has the same overall resistance or impedance to the supply. Okay, so in this case it's a DC supply, so we just talk about the resistance. But it really helps to redraw the circuit. Okay, this is such a simple circuit that sometimes it doesn't seem like maybe it's all that important, but as the circuits get more complex, you really need to redraw every time you simplify. Okay, so now we can calculate then our total resistance here. We have two resistors in series, so we're up here to this circuit. So this is going to be R1 plus R equivalent. And so that is just 1 ohm plus another ohm, right, which gives us a total resistance of 2 ohms. So we can again redraw the circuit now, where we have our 10 volt supply feeding one resistor of 2 ohms. And so using Ohm's law, we could calculate the supply current, or the total current, is equal to the supply voltage E divided by the total resistance, Right, so we have 10 volts divided by 2 amperes, or excuse me, 2 ohms, which gives me 5.00. So if we're putting this in Blackboard, it's going to have to be 3 significant digits, 5.00 amperes. Okay, so that would be our answer for this particular circuit. So we have a current of 5 amperes. That's our total current. Now that's going to come over here back to our main circuit. So back to our main circuit here, it's going to, the current is coming in here, so we have 5 amperes coming into this node point right here, call this point A, and it's going to split off, and part of it's going to go through the top resistor, and then the other part is going to go to the bottom resistor. Now, since these are exactly the same, hopefully it's obvious that these are going to split equally. However, if you want to do it mathematically, let's look at the voltage drop. Okay, so this is point A here, and we'll call this point B. So then if we look at this equivalent circuit down here, there's my point A and my point B. So we can calculate the voltage drop, VAB, which, since these are equivalent, that's going to be the same voltage drop over here. So we could find the voltage drop. And so VAB, that voltage is going to be, using Ohm's law, it's going to be the resistance of this equivalent times the current. And since in this circuit here, the current does not split, it's just a series current, it's just the 5 amps. So that would be I supply times R equivalent. And R equivalent was up here, which was at 1 ohm. So we had 5 amperes times 1 ohm. And so that, of course, gives us 5 volts. Okay, so the voltage drop here is 5 volts. And so therefore, we can use Ohm's law now to find the current through just this one resistor. We have 5 volts across this resistor. 5 volts divided by the resistance, which is 2 ohms. So the current through just this one resistor here is going to be 2.5 amperes. Okay, so that was using Ohm's law. And so we could do the same thing over here. We know we have 5 volts because these are in parallel. VAB, it says the voltage from point A to point B is the same. And so it's 5 volts across the top resistor. It's also 5 volts being dropped across the second resistor. And so again, using Ohm's law, we get 5 volts divided by 2 ohms, which gives us 2.5 amperes. So coming into point A, we have 5 amperes coming into point A, and 2.5 amperes are splitting and going through the top resistor, and 2.5 amperes are coming down through the lower resistor. Those then come over here through the resistors, coming back into point B. You got 2.5 coming up, 2.5 coming down. They join back together, and you're back to your 5 amperes that continues on around and into the negative of our battery. Okay, so we had a total equivalent resistance of 1 ohm for this parallel branch. We had a total resistance for the entire circuit of 2 ohms. We had a total supply current of 5 amperes. And we had 2.5 amperes running through each of those resistors. So now we have the exact same circuit. The only difference is that I've changed my supply. So I've taken and I'm applying an RMS 10 volt source, and I'm using it as a reference, so my angle is 0. All right, and so I've swapped out the DC battery supply for an AC supply here. So again, this is the RMS value. It's the phasor. But the resistors are the same. So now when we're talking AC circuits, we talk about impedances. But and so in the DC circuit, we had the series resistance was just the sum of all resistors in series. And for AC, when we talk about impedances, it's exactly the same. Only we replace the R's with Z's because we could have reactances in there also. But the equation is really the same. And then for parallel, for DC, right? This was for DC only, was the resistance. We would have that we have 1 over R1 plus 1 over R2 and so on. And so for AC, if we have a parallel impedance, we have the exact same form of the equation. We just have Z's because we could have reactances inside of this circuit. Now again, in this particular circuit, I'm just starting off. I don't have any reactance. I only have resistance. Okay, but so we can come over here and we can take and simplify this by putting in a equivalent resistance here, so which will give us our new circuit, where we would have R1, which was 1 ohm, and then we're going to have this equivalent resistance, okay, and that equivalent resistance would actually be an impedance equivalent for these parallel resistors. And we could redraw our circuit then, and it would look just like it did for the DC circuit, except for, of course, we have an AC supply. So we can calculate that this Z equivalent, all right, is 2 resistors in parallel. And so that is going to be 1 over 2 ohm, 1 over 2 ohms plus 1 over 2 ohms. Okay, there's no phase angles because we only have resistances. And so that gives us 1 over 1, right, or simply 1 ohm. So we have 1 ohm here. So then Z total is these two in series. Okay, so Z total is going to be the R1 plus the Z equivalent, which is 1 ohm plus 1 ohm, which is going to be 2 ohms. And again, if we're going to put this in Blackboard, we need to put our 3 significant digits. Okay, so if it comes out to be an even value, we still need our 3 significant digits. All right, so given that, we can now apply Ohm's law. Ohm's law tells us that the current, the supply current here, IS, okay, or IT for I total, if you want to think of the total current being supplied, however you want to think about it. That current is, using Ohm's law, it's E, which is now phasor, divided by our total impedance. And so that's going to be 10 volts, angle 0 degrees, divided by a resistance of 2 ohms, which is an angle of 0 degrees because it's nothing but resistors. And so that gives us 5 amperes at an angle of 0 degrees. So again, if we're going to put this into Blackboard, it's going to have to be 5.00 amperes at an angle of 0.00 degrees. That gives us our three significant digits. Okay, we have three digits, 5.00, that's three digits, and 0.00, that is three digits. Okay, so we can now come up here like we did with our DC circuit. We marked points A and B. Okay, so we can define the voltage VAB. Okay, but now this is a phasor voltage, but if we use this equivalent circuit here, we can find that the voltage VAB is going to be our supply current. All right, so we use Ohm's law, so we're going to have our supply current times our equivalent impedance, the equivalent. So that's going to be our 5 amperes at an angle of 0 degrees, and we're going to multiply that times our Z equivalent, which was 1 ohm, and so that of course is going to give us 5 volts. Okay, so if we're putting it in Blackboard, it would be 5.00 volts at an angle of 0.00 degrees. Okay, and so that is our voltage drop across these resistors. And so we can therefore also calculate the current through those resistors. So the current through resistor 2 is going to be the voltage, which is voltage VAB, divided by the resistance of R2, or the impedance Z2, but it's just a resistor here. And so that's going to be VAB was 5 angle 0. We're going to divide that by 2 ohms, right? And so that's going to give us 2.50 amperes at an angle of 0.0 degrees. And of course we could find the same out for I3, right, which is again VAB, but dividing by impedance or resistance, in this case R3, is going to be 5 angle 0 divided by the 2 ohms, which of course is 2.50 amperes at an angle of 0.00 degrees, if we want to put it in Blackboard with our three significant digits. So again, at point A, we have 5 amperes angle 0 now, because it's a phasor current, an AC current. So we have 5 angle 0 coming in. It's going to split off. And so when it splits off, then we're going to have 2.5 amperes angle 0 going up, and then 2.5 amperes angle 0 going down, going through the resistors, and then they're going to come back together at point B, and then through the rest of the circuit we're going to have our 5 amperes returning back into our supply. Right. So this, this is the AC, this is the DC. So the only difference here is the fact that we had to keep track of our phase angles. It was really, really easy in this case because the impedance of the circuit was resistance only, and resistors are always in phase with the voltage through a resistor is always, the voltage across the resistor is always in phase with the current through the resistor. So now we have the exact same AC circuit, only our resistors are now inductors. So we have 3 inductors with the same parallel, series parallel type of circuit, same values. But again, these are inductors, and so what they're giving us here is the inductive reactance. So remember, there's really a J phase angle with each one of these. Okay, so they don't show us that in the book. They just say, we can tell that it's an inductor by the electrical symbol. So we know that there's going to be a J term here. All right. So, but again, when we're looking at series impedances, you just add those together. And when you're looking at parallel impedances, you get the 1 over, just like you did for a standard DC circuit. So that's the nice thing. It doesn't really, the equation, the form of the equations is exactly the same. So all we have to do now is calculate these angles. So just as a reminder, before we get into it, we have Eli the Iceman. Okay, and that tells us that for an inductive circuit, the voltage is going to be ahead of the current. So when we complete our calculations, we need to kind of double check that the current is ahead or behind the voltage, is lagging the voltage. Okay, so the voltage lags, or the current lags the voltage in an inductive circuit. And remember, we're using our voltage supply as our reference, so it has an angle of 0 degrees. So we can again redraw this circuit, and so we just have the impedance X of L1, which is 1 ohm, and then we're going to have this equivalent impedance here, which again, it's a reactance in this case, X of L equivalent, which is a resistor or an inductor that in series and here. So we can calculate this. We're actually going to get the same calculation we had before. So the Z equivalent now, okay, is going to be the 1 over 1, but now we have a J. So there's a J2 here plus 1 over J2, which is going to give us 1 over 1 over the J. Okay, so if we actually did that, then it would actually kind of give us a minus J up here. But then we do a 1 over J again, and that just gives us J1. So we have J1 ohm. And again, if we wanted to put that into Blackboard, it would be J 1.00, and then our ohms for our unit. Impedances are opposition to current flow, and the unit for that is ohms. All right, so this gives us 1 ohm here. Again, these are actually inductors, so they need J's associated with them. And so we can now find our total supply current. Okay, so our total supply current, IS or IT if you prefer, depending on your assignment there. But the supply current is going to be our voltage divided by our impedance. Total, the impedance total, Z total, is just the sum of these two. So Z total is going to be J1 ohm plus J1 ohm, which is going to be J2 ohms. Okay, so we take that and we have our voltage, which is 10 volts, angle 0 degrees, divided by J2 ohms. Okay, or we could rewrite that. Remember that J is a positive 90-degree phase shift. All right, so that would give us 10 volts divided by 2 at an angle of plus 90 degrees. And so when we do the math there, we have 10 divided by 2 is going to give us 5. And then the angles, remember you subtract the angles in the top minus the angles below. And so that's going to give us 5, and this is amperes, it's a current, 5 amperes at a minus 90.0 degrees. Okay, and so that is our total supply current. All right, so looking at the voltage across this parallel branch here, we've been calling this VAB, right? And so VAB is simply Ohm's law, so it's a voltage. It's actually a phasor voltage, so I put the line underneath there to mark the phasor. VAB times I supply times the equivalent reactance there. Okay. And so again, that is now we're at 5 amperes at an angle of minus 90. So again, remember the minus 90, the current is behind the voltage, times R2 times J, or, you know, it doesn't matter really if you put the J in front or behind there, but J2 ohms. And so if we write that in angular form, we have 5 angle minus 90 times 2 angle plus 90. Okay, these are being multiplied, so the angles, these are being multiplied here, so the angles add, but this is a minus 90 and a plus 90, so we're going to end up having 5 times 2. I'm sorry, this, we're using the equivalent here. The equivalent was 1.0, not 2. Sorry about that. So I wrote that down incorrectly. 5 times 1. Okay, so that's going to give me 5.00 volts at an angle of 0 degrees. Okay, so this VAB up here, VAB is 5 volts at an angle of 0 degrees. Okay. All right, so given that, we can find the current through one of these inductors using Ohm's law. We know the voltage, we know the reactance. So again, we just apply Ohm's law. So we can calculate if this is like XL1 here. So we could say the current, I'm sorry, that can't be a 1. This was a 1 over here. This is our 2, our second inductor, L2. Okay, so XL2, so our current for inductor L2 using Ohm's law, again, current is equal to the voltage. So in this case, the voltage is VAB because it's the voltage being dropped here. So VAB divided by the reactance, or the officially the impedance, but in this case it's just a reactance, okay, X of L2. So that's going to be our 5 volts, angle 0, divided by J 2 ohms. Okay, and so again, if we put that in polar form, 5 volts, angle 0, divided by 2 angle plus 90, and so that's going to give us 2.5 volt, 2.5 amperes, so 2.50 amperes at an angle of minus 90 degrees. Okay, so in Blackboard we need 3 significant digits for that. So 2.50 amperes at an angle of minus 90 degrees. And since the third inductor down here, L3, is the exact same value, it's the exact same calculation. So you get 2.5, but now it's with an angle of minus 90 degrees for your current. 2.5 amperes at an angle of minus 90 degrees going up, 2.5 amperes at an angle of minus 90 degrees going down. Those go through those 2 inductors, they join back together, and we're back to 5 amperes at an angle of minus 90 degrees going back into our supply. So here we have the same basic circuit again, only this time we have capacitors. So we know again that we have capacitive reactances are going to have a minus J or a minus 90-degree phase shift with them. Okay, so we have the same type of circuit that we've been discussing, but we have the capacitors. So again, we're going to have our equivalent here where we're going to put in a impedance equivalent. So Z equivalent is going to be 1 over the minus J2 plus 1 over the minus J2. And so if you solve that, you would actually end up getting like 1 over J1, and that 1 over then makes it a minus J1 ohms. So our equivalent impedance would be minus J1. So if I'm going to put that into Blackboard, it would be minus J1.00 space and then ohms. So that gives us this equivalent kind of circuit we had here before. So we still had the first capacitor. Oops. So used to drawing resistors. Okay, so we have our first capacitor minus J1, and then we have this equivalent one minus J1. And so we can talk about the total impedance now is minus J1 plus a minus J1, right, which is going to give us minus J2 ohms for our total impedance seen by this supply. So then we can calculate our supply current. Our total supply current, IS, is going to be the E divided by the Z total, which is going to be the 10 volts angle 0. Again, we're using this as our reference. And so that's going to give us, we're going to divide by minus J2 ohms here. So we're going to have our 10 volts angle 0 divided by 2 at an angle of minus 90. And so now this is going to give us a 5 ampere current with an angle of plus 90. So I'm putting the 3 significant digits for Blackboard there. So again, remember Eli the Iceman. In this case, we have the capacitor, so our current is now ahead. So we have a positive 90. Our voltage is at 0. That's our reference. So our current is ahead by 90 degrees through this. This is our main current. So coming out of the top, we've got 5 with an angle of plus 90 degrees, and also going in underneath, we have that. Okay. So then we can calculate our voltage VAB. So our voltage VAB here, okay, and using Ohm's law again, right, VAB, okay, Ohm's law, it's the supply current times the equivalent impedance, okay, and because we're only looking for this voltage, so that's going to be the supply current 5 at an angle of plus 90 times the equivalent reactance, which is minus J1. I'll try to put the correct one in this time. So minus J1. Okay, and so we can rewrite that in polar form. Plus 90 times the minus J is a minus 90, so that's 1. But at an angle of minus 90, okay, so remember the angles add when you multiply, so you end up with 5.00 volts at an angle of 0.00 degrees. Okay, that's my 3 significant digits for Blackboard. 5 volts at an angle of 0 degrees. So that is our voltage drop, VAB here, across these two parallel capacitors. So therefore we can calculate the current through each one of these. So call this capacitor C2 and C3. So the current through I C2, that second capacitor, right, using Ohm's law, is going to be the voltage across it, which is VAB, divided by the total impedance, which is just the reactance of minus J2. Right, so X of C2, I'll write out the variable first, and then we'll put in the values. So we're going to have 5 volts at an angle of 0 divided by minus J2, which is 5 volts, angle 0, divided by 2 at an angle of minus 90 degrees. And so that's going to give us 2.50 amperes at an angle of plus 90.0 for 3 digits degrees. Okay. So that is that current. Splitting here at point A, we have 2.5 amperes at an angle of plus 90 going to come up, go through this capacitor. We're going to have another 2.5 amperes coming down below, going through the lower capacitor. They're going to join back up at point B to the total of 5 amperes here, angle plus 90 degrees, and back into our supply. Alright, so I went through that capacitor circuit very, very quickly because it was just pretty much a repeat of everything that we've done with the previous 3 circuits. But this circuit here, even though it has the exact same shape now, notice that here the inductor is over here. So we have an inductor, we have a capacitor, and then we have a resistance. Okay, so now we're going to have to be a little bit more careful because we're definitely talking about impedances here. We're not talking about just reactances of the same form or just resistances. Okay, so we have a little bit of everything in here, and they're just kind of scattered around. Okay, and this is about as simple of a series parallel RLC circuit as you can get. Okay, so now remember we're going to have our equivalent impedance here. So I'm going to start off by drawing that equivalent circuit down here, and so we're just going to have this inductor down here, which is plus J1, and then for this we're going to do an equivalent impedance here, but I'm just going to draw it as a box. We're just going to call this Z equivalent here because it's going to have some resistance and it's going to have some reactance in it. So we'll just call it a box. You know, and if you wanted to, you could even box this one up, okay? And and then we're going to have a total, okay? And I didn't even draw this in the last couple there, but we're just going to have like a total, Z total, which is just going to be a box with a little bit of reactance in it and a little bit of resistance in it. Okay, so we're just going to have, those are our equivalent circuits that we're going to build. So let's look at the Z equivalent here. Okay, so the Z equivalent has the capacitor in parallel with the reactance. All right, so we're going to get a 1 over 2 ohms plus 1 over a minus 2 J ohms. Okay, so we got this minus J on this side now. So if you calculate that, then what you're going to find is that the total is going to be Z equivalent is going to be 1 ohm minus J 1 ohm. All right, and so if we wanted to look at the polar form of that, right? It's actually going to be the square root of 2 at an angle of minus 45 degrees. Okay. So that is giving us a 1. If we're going to put it in Blackboard, it'd be like 1.00 ohms minus J 1.00 ohms. That's the rectangular form, and if we wanted to put it in the polar form, it would actually be the square root of 2 at an angle of minus 45 degrees. Okay, and so if we're going to put that into Blackboard, it would actually be 1.41 ohms at an angle of minus 45.0 degrees. Okay, but remember, square root of 2 is 1.414. 2. So you should keep all five, at least 5 significant digits when you're doing that calculations. Okay. So so that gives us this equivalent in impedance now. And so we can calculate the total impedance then is going to be the first impedance. This one was the first impedance plus this equivalent impedance. And so that is going to be J1 plus 1 minus J1. Okay, and so when we add that up, and it's actually in this case, you know, adding up in rectangular form works very nicely because we're simply left with 1 ohm. Okay, so we're left with 1 ohm. There's no J. We had plus J1. We have a minus J1. They disappear, and we are simply left with 1 ohm. All right, so now we can calculate our supply current, I supply, and our supply current therefore becomes the Ohm's law says that we're going to take E divided by Z total to get that supply current. So we're going to have our 10 volts, angle 0 degrees, divided by simply 1 ohm. And so our current now, I, is going to be 10.0 amperes at an angle of 0 degrees. That's our total. This is our total supply current. Okay, so that is our total supply current there. Okay. 10 amperes at an angle of 0.00 degrees. Now, I want to just take a minute out here and discuss this. So what's happening here, let's return back up here. We had this impedance was plus J1 ohm, and the equivalent of that capacitor piece was minus J1 ohm. So these values were equal. Okay, these values are equal. This is what we call resonance, and weird sort of things happen at resonance, right? Because as you can see, these two cancel out. These two actually canceled out, and we were left with what appears to be nothing but resistance to this. So this voltage supply sees nothing but resistance in this circuit, and so that's why there's no phase shift in the current. Okay, this voltage supply can't actually tell that there is an inductor and a capacitor in the circuit because these two are matched, and what they're doing is they're passing energy back and forth. Okay, so let's find out. We haven't actually done this before, but if you go back and look at the previous circuits, I didn't make a point of this, but if you look at the voltage of this circuit here, this is our original DC circuit, right? We did calculate that we had 5 volts DC across these resistors, and since we had 10 volts here, right, that meant that we actually had 5 volts across this first impedance also. But let's calculate what this voltage is now. What is the voltage across this inductor? Okay. And so we know we got 10 amps going through it, and it has 1 ohm of reactance. And so using Ohm's law, right, we can calculate 10 amperes. Okay, so VL is going to be the current through it, which is the total current, the supply current, times the J1 ohm there, right? And so that's going to be 10 amperes. So that's going to be 10 amps angle 0 times J1. Okay, and so that's actually, right, J1 would be saying like 1 at an angle of plus 90 degrees. And so we're going to find out that the voltage right here is actually 10 volts at an angle, okay, so 10.0 volts, but at an angle of plus 90 degrees. Okay, so remember our supply voltage is 10 volts, but it's at an angle of 0 degrees. But over here at this inductor, we also have 10 volts, but it's 90 degrees ahead of this guy. Okay. All right, so then let's go on and calculate. We had, as we did before, we had points A and B here. So we had A and B. And so we can calculate VAB, as we did before. We have VAB, which was the supply current. We're looking kind of at this equivalent circuit down here. The supply current times this equivalent impedance. And so that was 10 amperes times this equivalent. And remember, the equivalent here is 1.0 at an angle of, or 1 ohm minus J1 ohm, right, which is in polar form is 1.4142 at an angle of minus 45 degrees. Okay. And so then if we calculate that, we got 10 volts times 1.4, or 10 amperes, sorry, 10 amperes times 1.412 ohms, which is going to give me 14 volts at an angle of minus 45 degrees. Okay, so I actually got 14 volts over here. I got 14 volts across this capacitor now. Okay, and so if we're going to put that in Blackboard, remember it would be 1.41 volts at an angle of minus 45.0 degrees. Okay, so if we're going to put it in a Blackboard, we need to drop it down to 3 digits. But when you're doing your calculations, keep those 5 digits, otherwise round off. You might have a little bit of round off error. All right, so now we can calculate the current in there. Okay, well, let me just talk one more time about this. Notice that we have 10 volts coming in. We're supplying 10 volts. And yet we've got 10 volts here. And now we've even calculated we got 14 volts here. And again, this is the resonance thing, because the capacitor voltage, right, the capacitor voltage is actually 45 degrees behind the supply voltage. And the voltage across the inductor is 90 degrees ahead of the supply voltage. And so what's happening is these two are kind of playing hot potato, sitting here passing their energy back and forth, back and forth. And so, you know, with AC circuits, you have to be careful because you can have voltages that are above the supply voltage. Because now when you first turn on a circuit, remember there's a transition phase where a transient phase where you're charging up the capacitor and the inductor and you're putting that energy in them. But once you hit steady state now, that energy is in the capacitor and inductor, and they're sitting there passing that energy back and forth between each other. And that gives us, that's kind of where this extra, what seems to be extra voltage is at. It's this energy being stored and then released and then stored again between the capacitor and its electric field and the inductor and its magnetic field. All right, so we can go ahead and we could calculate the current through the capacitor now. The current through the capacitor would be the voltage VAB divided by the reactance, which is minus J2. And so we're going to have a 14.142 at an angle of minus 45 divided by the reactance of the capacitor, which is 2 at an angle of minus 90, which is going to be 7.07 amperes at an angle of plus 45 degrees. Okay, so 7.07 at an angle of plus 45.0 degrees. So that is the current flowing through the capacitor. Okay, but the voltage through the resistance now, we're going to have to calculate that because it's different in there. So we'll calculate the voltage across, or the voltage across the resistor is the same as the voltage across the capacitor because those are in parallel, but the current through the resistor, we're going to have to calculate that. So the current through the resistor, IR, is VAB divided by R. Okay, so VAB is the 14.142 volts at an angle of minus 45 degrees. And the resistance is simply 2 ohms, right? And so the current through then is going to be 7.07 amperes at an angle of minus 45.0 degrees. Okay, so the current coming down through the resistor is 7.07 amperes at an angle of minus 45 degrees, but the current going through the capacitor is 7.07 amperes at an angle of plus 45 degrees. So let's take a moment to review Kirchhoff's current law. So remember, Kirchhoff's current law says that the sum of the currents coming into a node is equal to the currents leaving the node. And so, you know, if we look at this, I calculated up here that I had 10 amperes as my supply current. So IS was 10 amperes angle 0. So let's draw this out. Okay, so here is my 10 amperes at an angle of 0. Okay, so this is my supply current. And now I said, here's my capacitor current. Okay, so my capacitor current is going up this way at 45 degrees. At 45 degrees, and it has a magnitude of 7.07 amperes. And then we had our resistor current, which was at minus 45 degrees. So if we start at this point and we go down at an angle of minus 45 degrees and we go at 7.7, okay, so this was IR here, okay, which is 7.07 at an angle of minus 45 degrees. And this was my capacitor current of 7.07 at an angle of plus 45 degrees. All right, and so if we take and we add this current to this current, right? So we have IC coming out through the top and IR coming down through the bottom, then we do in fact add back up to the supply voltage. The supply current, right? So the supply current was 10 amperes, angle 0, and so the supply current IS is equal to IC plus IR. But remember, these are all phasors, so you have to pay attention to those angles. But remember, Kirchhoff's current law, KCL, always applies to any point in the circuit. Current coming in must equal the current leaving. All right, we're going to look at one last circuit permutation, if you will, of this. So here we have the Rlc circuit, the same form of the circuit we've been looking at before, but now we have the resistor is in series with the supply, and then we have the capacitor is up here in parallel with the inductor. Okay, so again, we would come up with an equivalent circuit where we would have this impedance here, which is just the resistor. Z equivalent 1 if you want, and then we would have the reactance equivalent circuit. Okay, and then we could redraw this one more time to just have one Z total impedance. Okay, and I'm drawing boxes now because these could have some kind of reactance. There might be some resistance in there or whatever. So I just using boxes to indicate these reactances. Okay, but we're going to take and we're going to find the equivalent of these reactants here. I'm going to call this Z equivalent X, right? And they're in parallel, so we know that we get 1 over. Now they're both 2 ohms reactance, but the capacitor is minus J2 and the inductor is plus J2. So we're going to get 1 over minus J2 plus 1 over positive J2. And so if I try to do the math here, okay, we've got a plus J and a minus J there. So if we bring the J's on top here, all right, we would end up having like a 1 over a plus J times 1/2, and then we bring this one on top, that would give us a minus J 1/2. So we have a plus half a J minus half a J, which gives us a 1 over 0. Okay, so 1 over 0 gives us what we like to call infinite resistance. Okay, so the resistance would be infinity. And if you don't remember quite how that works, think about this. Yeah, I know the mathematicians tell us we can't divide by 0. But you need to consider the fact that, when this says 2 ohms, it may actually be off a little bit. So let's just take a look. If I take 1 divided by 1, right, that of course simply gives me 1. If I take 1 divided by a smaller value, call it 0.1, that would give me 10. If I take 1 divided by 0.001, right, that gives me 1,000. So if I was to take like 1 divided by 0.000001, that would give me 1,000,000. Okay. And so what happens is, as you divide by a smaller and smaller number, you get a larger number. And so that large number is infinity. So infinity here, infinity, okay, write it out for you. Infinity is just a really big value. Really, really big value. Okay. And when you divide by a really big value, then you get 0. Okay, so like if you if we go the other way here, right, if we have 1,000,000, if we divide by 1,000,000, then we are left with 1 micro. Okay, so if you divide by a really big number, then you end up with a really small number. All right, and so that's all infinity is saying. It's just saying that, hey, this is just a really, really, really big impedance. Okay, so we don't have an undefined impedance. What we have is a really, really large impedance. So this is kind of an interesting case, and again, this is something we call resonance here, because we have the magnitude of the capacitive reactance is equal to the magnitude of the inductive reactance. And so this here is what we call resonance. Okay, and this is resonance. In this case, it's what we call parallel resonance because the capacitor is in parallel with the inductor. And so a lot of times they call this a tank circuit. All right, and they call it a tank circuit because it's like current gets in here, but it can't get out. Because as I stated before, these guys are playing hot potato. I don't know if I can draw a potato here, but if you think of the electrons as potatoes, the capacitor and the inductor are playing hot potato, passing this back and forth, back and forth, back and forth. And they don't care about this guy over here and what he's trying to do, because these guys got charged up. They have all this energy in them, and they're just dumping that energy back and forth and back and forth. And they're just dumping this energy back and forth. And so they're not allowing the current to actually flow through the circuit, because they're like, okay, you gave me some current, now I'm going to dump it back, and the inductor catches it, and then the inductor says, oh, I'm going to pass that back to you, and these guys are just sitting there passing their energy back and forth. And so we actually get this special case here of a parallel resonance circuit, also known sometimes as a tank circuit, where these guys are passing back and forth each other, and they look like infinite resistance. Okay, really, really big resistance. All right, so if that's the case, then this resistance is effectively infinity. Okay. So if we were to try to calculate, by the way, these had J's in them, right? But you had half a J minus half a J. The J's disappeared, so you're just left with nothing. Okay, so there's no J, there's no phase angle in here. And so our total impedance then is going to be our resistance of 1 ohm plus our infinite resistance of the tank circuit. All right, and if you add 1 to infinity, you get a slightly larger infinity. So it's infinite ohms. So now if we try to calculate the supply current, the supply current now is our voltage divided by our total impedance. Okay, but again, our total impedance is infinity. So we're going to have some finite number of 10 volts angle 0 divided by infinity, which is going to give us a current of 0 amperes. So 0.0 amperes at an angle of 0.0 degrees. So this guy is doing nothing. He's got nothing to do here but watch this capacitor and inductor play hot potato. That's all he's got to do. Okay. However, let's look at the voltages. So remember here we have voltages. We have a voltage across the resistor. Well, according to Ohm's law, right, the voltage is equal to the current times the resistance. And so if the current is 0, then the voltage drop, VR, is simply 0. So the voltage drop there is 0 volts at an angle of 0.0 degrees. Okay. But if we apply Kirchhoff's voltage law, we have 10 volts here, angle 0. We have 0 volts here, angle 0, which leaves us with 10 volts, angle 0 across our tank circuit. Okay, so we have 10 volts across our tank circuit. So let's look at the current in the capacitor. The current in the capacitor is the voltage VAB divided by the reactance of the capacitor. So the current in the capacitor is VAB divided by the reactance minus JX of C. So that is 10 volts angle 0. Again, where did we get this 10 volts angle 0? Well, if we applied Kirchhoff's voltage law and there's no voltage drop across the resistor, then there must be 10 volts dropped across the capacitor and inductive circuit. So we have 10 volts there divided by 2 ohms at an angle of, it's a minus J, so it's an angle of minus 90 degrees. So we're going to have a current of 5 amperes, 5.00 amperes at an angle of plus 90 degrees inside of our capacitor. And if we look at the current in the inductor, we're going to have VAB divided by plus JX of L, which is 10 volts angle 0 divided by 2 at an angle of plus 90. So the current through the inductor is also going to be 5 amperes. 5 amperes, but at an angle of minus 90 degrees. Because remember Eli the Iceman? Right? The voltage is ahead of the current in the inductor, and the current is ahead of the voltage in the capacitor. Okay? And so these guys are at 5 amperes. We have 5 amps flowing through this. We've got 5 amps flowing through this and 5 amps flowing through this, but their angle is minus 190. So let's look one more time at Kirchhoff's current law. Okay, so Kirchhoff's current law says, okay, well, I got 0 amps coming in here. But we have our capacitor current, IC, and we have our inductor current, IL. And I'm telling you that those are not 0. So what is happening? Well, if we draw the phasor diagram, right, we have the capacitor is 5 amperes at an angle of plus 90. And then if we draw the inductive, so we start right back here, we draw the inductance. Let me maybe put that one in blue, I guess. Okay, so if we take this one here, and that's going to be 5 at an angle of minus 90. So as I said before, these guys are basically just sitting here playing hot potato, passing their energy back and forth between them. So our total current is, as we calculated, right, we have plus 5 going up, 5 going up in the straight up, and then 5 coming straight down. So our total current is actually 0. Okay. And so that is verified by Kirchhoff's current law, KCL. All right, so again, this is a special circuit here called a tank circuit, which uses parallel resonance, where the reactance of the capacitor has the exact same magnitude as the reactance of the inductor. And so we do have current flowing through the capacitor and the inductor. These guys are sitting here passing their energy back and forth. Okay, but there's effectively no current flowing through this resistor here. Okay, so this tank circuit looks like an infinite impedance.